Hi everyone, this is my voiceover of Laplanda Tech programming in LabVIEW videos that I originally created for my overseas audience, and now, since there is some interest from my Silicon Valley community, I decided to quickly translate it. If you're coming from text-based programming, welcome to a world where data flow is visible and debugging feels less like archaeology. In the previous episode, we compared different database management systems. In this episode, we will break down SQL commands inside our function. As you can see, we now have a new button called SQL Query. Here we will write a pure SQL command and we will compare how much simpler things are when an SQL function is already programmed. This is usually the moment when LabVIEW developers smile quietly while SQL strings behave exactly as expected. So we stopped at the logic that we use to make our buttons active or inactive. The buttons that we cannot use at a given moment we make disabled and gray, and the ones we need, on the contrary, we activate. If this diagram seems complicated or confusing to you, we can simplify it. I prepared two options showing how this can be done. In LabVIEW, even disabled and gray is a design decision, not a side effect. I wrapped all my disabled property nodes into a diagram disabled structure. Why? Because later on I will remove the disabled state entirely and leave only enable. Why did I leave the disabled state for now? So that it would be easier for you to compare and understand what is happening. Right now, it is more important for us how clear the diagram is, not how it looks visually. But this is up to you, what is more convenient for you or what you like more. So, in both the disabled and enabled cases, I have exactly the same programming logic, and its meaning is written directly in the name of the case. Disable controls for login. Both cases perform the exact same action. Here I showed you an example of how this logic can be wrapped into a sub-VI. For demonstration purposes, I created two sub-VIs, meaning that part of the functions is in one sub-VI and another part is in the second sub-VI. When logic is identical, LabVIEW lets you prove it visually, no comments required. In the first sub-VI, we use a cluster, and in the second one, we use direct connections to terminals. Other programming approaches are also possible, but for now, we'll focus on these two. In these sub-VIs, we use references to our buttons and values as controls. Let's first look at the second sub-VI. When we wrap our property nodes into a sub-VI, the sub-VI automatically creates control over these property nodes through references. Let's see how this happens. I select the property nodes, then edit, create sub-VI, and to make it easier to see, I choose vertical compress. Auto-generated references are one of those features that make you wonder why you ever managed UI state manually. And now the sub-VI is created, all that's left is to save it. Here I can align the diagram the way I like if I have extra time. If I don't have extra time, I can use cleanup and also label the icon. We've already done this in previous episodes. Here we already have all the references. They are created automatically and already connected to the terminals. It's important to know that the maximum number of terminals is 24. So sometimes it makes sense to use a cluster. We'll look at that now. For now, I close this sub-VI. We don't need it anymore. LabVIEW offers to save it, but we only have one option, defer decision. Why defer decision? Because this sub-VI has already been created in the background, and when I return everything back to its original state using Ctrl-Z, I'm asked, do you still want to save this sub-VI? I don't need it, so I choose don't save or defer decision. Now, let's look at the sub-VI that uses a cluster. As you can see, the cluster is already created here. We already discussed how to create clusters, but I'll briefly remind you. For example, I take several references, choose NXG style, data containers, cluster, and place the references inside it. And on the block diagram, here is our new cluster. I connect it to the function unbundle by name. I expand it and we can see all the references. Now I delete this because I don't need it anymore. Clusters in LabVIEW are basically structure with a seatbelt. Now we need to create a constant for our cluster, which we'll later use when creating a similar cluster on the main block diagram. To do this, I right-click on cluster 1, create constant, and double-click to minimize it. We move it to the main block diagram, and now we already have the constant here. I just want to show how to expand it. We select bundle by name from the cluster functions and connect it to the cluster. In this case, the order doesn't matter to us, but in general, you can change the order. If you click here, you can see and rearrange it. For us, it doesn't matter, so we leave the references in this order. And we already know how to obtain a reference. For example, I go to Find All Databases, choose Create Reference, and I can connect the Boolean Find All Databases to the terminal with the same name. Now I don't need this anymore, so I delete it. If you can wire it, you can control it. That's the LabVIEW rule. So we've looked at several variants of the same code, and as they say, there is no bad code, only code that was misunderstood. And in general, there is no difference between theory and practice, except that in practice, there is. I no longer need the disabled structure, so I remove it by using remove diagram disabled structure. Since we already replaced it, I delete it. Now we move on to reviewing SQL commands in our functions. For that, I run the program. Let me close some extra windows. Okay. So the program is running. I log in as an administrator. How we log in, how we select a database and the table, we already covered this in previous episodes. So we go straight to our database search window. At this point, the UI is doing exactly what it's supposed to do, and that's not accidental. Here I want to find, for example, 1 and 2 in the index ID column. I press search, and the search program selects all matching values for me. Let's see how this works on the block diagram. I go to the wait for event case and the DB search event case. Here when the button is pressed, the command starts executing the following sequence. First, we check whether there is anything in the search field. If there is nothing, then using empty string path, we go to the true case. Here we get a pop-up window, 1 character min. Then we go to the enum case wait for event, which brings us to the timeout event, where we wait for the next command. It's worth mentioning that we set the loop speed to 100 milliseconds, which means 10 iterations per second. We don't really need high speed here, so we use this delay in order not to overload the processor with unnecessary work. Even your CPU appreciates good LabVIEW architecture. Now let's return to DB search. If there is something in the DB search field, we go to the false case and end up in the enum case DB search, which is located here. Here we see what data we need to perform the search. First, we need the table name. We get it from the DB table property nodes using the index array function. We find our position in the DB tables list, which we discussed in the previous episode. Then we select the column where we will search, then what exactly we will search for. This value is stored in the local variable db item to search. And we also have a sub-VI called db search table, which we'll also look at. So execution here, as usual, goes from left to right. The DB search string goes into search and replace string, where we remove all spaces that the operator might have accidentally entered. The clean string is then passed into string-to-1D array. This is the part where text-based programmers are still arguing about white space, and we are already done. This function, string-to-1D array, is not part of the standard function set. Just like in text-based programming languages, we can include additional applications, libraries, and files. Each library has its own functions, and this exists in LabVIEW as well. To get the library we need, we go to VI Package Manager. Here in our case, we use functions from the OpenG package. To install all the main functions, we use the OpenG toolkit. In my case, this package is already installed. Later, I'll show where it appears on the block diagram. Let's look at this function in context help. It converts a delimited string to a 1D array. The delimited character in our case is a comma. This 1D array then goes into a for loop. In this case, the number of iterations will be equal to the number of commas. Now, let's look at what the sort-like button is for. If the sort-like boolean is true, then part of our SQL code will use like. If it's false, then we use strict equal. This case participates in forming our SQL code. So, step by step, we open our database. Credentials were discussed in the previous episode. Then we execute our SQL command. It will run as many times as there are values separated by commas. After the for loop finishes, we output the column names again and collect all the data into the DB table indicator. Just like in any text-based language, there are outputs operators. For example, in Python there is print, in C++ there is serial print, and here we also have the ability to output intermediate data to the monitor. To do that, we place a probe on the wire where we're interested in. In this case, we're interested in the SQL command right after concatenate strings. Now let's press the DB search button and look at our SQL command. And yes, it's important to mention where this SQL command goes. It goes into one of the database connectivity toolkit functions, specifically dbtools select data. I press the button and we see our SQL command. This is one of those moments where you realize you didn't type a single line of SQL by hand, and yet it's right there, clean and readable. Let's see how the command changes if we uncheck the like boolean. We can see that the command changes. So our like button works. Now let's check how the sort numeric boolean works. For that, let's do DB table refresh and sort. We see that sorting is done by the index ID column, and all numbers are ordered numerically. This is numeric sort. Now, if we uncheck sort num and press sort by column again, sorting happens as if it were text. This is string sort. Let's see how this looks on the program level. We close the sub-VI and go to the case that is controlled by the sort button. It is located under wait for event and sort by column. Here we can see that in order to execute this command, we need the column number. We get it from the DB table columns control using the property node value. And here we use the function called 2D array sort. Let's look at its block diagram. Here we see the logic that allows sorting either numerically or as text. We have already discussed this earlier. Here it's important to say that we do not sort the entire table inside the database. We only sort the local table that is displayed on our front panel. Why do we do it this way? Because in a database, data can be stored and saved randomly, not necessarily in the same order in which we wrote it. This is a visual difference, for example, compared to Excel tables. With each update or addition to a database, the position of rows in a table can change, and therefore sorting tables directly in databases doesn't really make sense. Oh, and one more thing, here in parallel, we also reset the table colors to our default colors. And after sorting through wait for event, we return again to the timeout loop. The next function we'll look at is save txt. DB table saved in file. The table is saved into a file, and here we get a prompt showing us exactly where. Let's go to that folder and take a look at the file. The folder is called report table, and here we can see that the file has been saved. All column names and all data have been preserved exactly as they were in the table on the front panel. Here it's important to mention that we save the data as a delimited txt file for convenience, because not everyone may have Excel installed. I have OpenOffice installed, and in order for the file to open correctly, I must select comma-separated delimited character. And once we do that, we see that all columns are automatically formatted. We open the file and see all our table data, everything. This means that our txt file can be opened by any program with any extension installed on the computer, as long as it supports reading delimited spreadsheet files. Now, let's see how this looks on the program level. We go to the save txt case, and the very first thing that executes here is the to-button dialog, which asks us to confirm our intention to save the txt file. Save table to txt delimited file. After confirmation, the file is saved. The next sub-VI is executed, the one with the icon DB table save. Into this sub-VI, we first pass a 2D array string from the local variable DB table, as well as a 1D array string with column names from the DB table property node. Let's see how this sub-VI works. As usual, execution goes from left to right, and we see that we pass our data from DB table through a double for loop, where we search for commas and replace them with colons. We could use any other character instead of a colon, but since our delimited character is a comma, we must replace all commas inside the table so that they are not interpreted as delimiters by the write delimited spreadsheet function. In other words, we must remove commas everywhere inside the table so they are not treated as separators. Next, we insert the column headers into the first row using insert into array, and then we write everything as a 2D array string into the write delimited spreadsheet function. To create the directory, we use our standard approach with application path and build path. As usual, we check whether the folder exists, and if it doesn't, we create it. We already covered this in previous episodes. Then in the file name, we add time, and we format the time in a special way so that it doesn't contain alpha characters, meaning characters that Windows doesn't allow in file names. This way we avoid writing into the same file because the timestamp will never repeat. Let's place a probe and see what the string looks like. So here I need a probe after concatenate string and after build path. Then we press our button and see that the first probe shows the file name and the second one shows the full directory path where the file is saved. At this point, LabVIEW quietly did file handling, path creation, and formatting, while a text-based language would still be arguing about slashes and escape characters. The next button we'll look at is view size. This is a very important function, and here's why we must use it. As we already know, when creating a table, we define the cell size, and if the size of the data we enter, the number of characters, exceeds that size, then any changes we try to make will not be applied. In other words, when writing to the database, an error will occur. I press the view size button, and in this table we can see the cell sizes. For example, the index ID column has a size of 20, the voltage column has a size of 10, and the operator ID column has a size of 50. Now let's see how this function works on the program level. We find the terminal for this button on the block diagram. Here we see that the DB table column information in use table becomes either visible or invisible through property node visible. At this same time, we activate or deactivate buttons that are not needed when the view size button is pressed. We can see that when this button is active, some other buttons become deactivated. This way, we protect the operator from making mistakes. So where do the data in the DB table column information in use table come from? Where are these values written into this table? Let's find out. To do that, we need to look either for property nodes or local variables. Let's first look at the property nodes. This one and this one, we can see that the data is not written from here. So we need local variables. And here we immediately see that this is where the data is written from. First, in the first local variable, we write the initial state, an empty table when the program starts. In the second case, data comes from the dbCreateTable case, which we'll look at later. The third local variable is written from the addColumn case, which we'll also look at later. And the last write happens in the dbDeleteColumn case. So these are all the different cases in which our table is updated. The next function we'll look at is replaceCell. Let's replace some numbers. For example, in this cell, current in milliamps, I change 888 to 999 and press the Replace Cell button, selecting Replace in one cell. And we see that the data has been replaced in that cell. Now let's see how to do the same thing using SQL Query, the way users do it, for example, in PostgreSQL. We press the SQL Query button, and here we see a standard SQL command with the same goal as what we just did in one click. I already have it pre-formatted here, but if I had to write it from scratch, it would take more time and the probability of error would be much higher. So now let's replace the value in the same cell back from 999 to 888. I just need to carefully check all the numbers. Yes, we press Send Query, and we see that 999 has changed back to 888 in that cell. But of course, this took more time than simply pressing the already programmed Replace Cell button, even though the SQL function was pre-formatted in this case. That's it. I'm already tired, and you probably are too, so let's stop here for today. The most interesting part is still ahead. How we programmatically form SQL commands and how that compares to writing raw SQL code directly. If you've ever debugged SQL at 2 a.m., you already know why automation matters. Thank you for joining LaPlante the Tech. If you have any questions, please leave them in the comments. If you learned something new today, give this video a like and subscribe to learn more from upcoming episodes.